Okay, so we understand Runnable, how to do it with Runnable and how to do it with lambda expressions. In your assignment, you'll have the choice of doing using either of them. But let's try to understand what's going on here. So supposing my list is one of these operations that does eager evaluation. And I've got this compound list. How many threads will be created here? Four? Anybody disagree? So T1 to do this part, T12 to do this part, T2, T21, and T1 can do the list after T1 and T12 have finished, and T2 can do the second list after T2 and T21 have finished. Right? So 4 threads. Okay. And if I have to, so that is my first expression I entered. If I enter the same expression again, sorry, T1 to go and do the top level list. Okay. So because we are creating n minus 1 or n minus 1 threads given n expressions, we are doing a good job with saving number of conserving the number of threads created, and that's a good goal. Are we doing a bad job here in any way? Could we do better than the algorithm I've shown you in terms of thread creation? And not only thread, what about the joiner objects? You know, objects are expensive. So there are these thread objects I'm creating, there are these joiner objects I'm creating. Threads after they're created, they terminate. And the objects will be garbage collected, ultimately. Okay, so it's not as if we're doing something really, really bad by creating a lot of threads. But we still want to go and conserve the number of threads we create and the joiner objects we create. So that's why we went and allowed the parent thread to also compute something. But can we do even better? What's something bad we're doing here? For every expression that is to be evaluated, we create a new thread. So the user enters this expression, we created 4 threads. If the user enters, and again we create how many joiners do we create? We create, I didn't ask you guys that question, but we have to have 3 joiners here. Okay. So if I was to re-enter the same expression second again, I create another 4 threads, another 3 joiner objects. So the user went and entered this expression first, and then the user entered the second expression again later, and these 2 expressions are to be evaluated serially. It's not as if these 2 expressions have to be evaluated in parallel. Okay, the user entered an expression, wants to see the result, based on that result wants to enter another expression. Okay, and in this case I've just entered the same expression, which is kind of silly, but that allowed me, I could just copy and paste. But let's say the user enters the second expression again. We've gone and created another 4 threads, another 3 joiner objects. Okay. And ideally, what could we have done? Somehow reuse those thread objects. Okay. So that's going to be the challenge for the next 20 minutes. Okay. So we want to do the following. So minimum threads and joiner objects need. I'll have to do this all over again, but make sure that I don't. Okay, I won't click another time because I might go to the next slide. So what should we do? How should we? We still have these abstractions: thread abstraction, wait, and notify. What should we do? And this is not easy. If you can figure this out today in 20 minutes, we are doing really well. Okay, and like I told you, Andrew and I were on emailing each other till late last night to get this right? And there are languages that actually allow you to create such abstractions. So what should we do? Tell me all the things we need to do to sort of reuse the threads. Yeah. So have a thread factory or joiner factory. And the idea of having a factory is that when you go to a factory, you can get back an existing thread. Good. That's one concept. Let's go in more depth now. What else do we need to do? Yeah. Okay. Very good. So the idea of some long living thread. Okay. And this factory is going to be really a pool which keeps a list of long living threads. And we don't quite know how to create long living threads maybe, but creating long living joiner objects should not be hard. Okay, we just reuse those joiner objects later. Okay. So thread, you use the word pool. How many of you guys have heard the term thread pool before in your life? How about, so something you learned in 410, that is the super type of pool. What kind of object is a pool that you might have seen in data structure course? Table means that you need a key access, but what's a super type of table? Stack? Well, we could do stack. So stack and table, the super type is collection. It's some kind of collection. Okay? We could do a stack or we could do a queue. Okay? And those of you who run operating system, we could do a bounded buffer where there's only a bounded number of these. But basically a collection of some kind. Okay? And we'll go and implement it as a queue. It can implement as a stack also. Okay? So how do we get, and again, I want this to be coming out as much from you as possible because I'm going to give you the details, so it'll be boring that way. How do we get these long-lived threads around? What does that really mean to have a long-lived thread? And it means a lot of things. So what is the first thing that comes to mind? Right now, okay. Sorry? So it doesn't terminate when it finishes execution, which is kind of right and kind of contradictory, right? So Mac?
I think he means like it doesn't get garbage collected when it terminates.
It doesn't get garbage collected when it gets terminated. So we keep a reference to it, fine. But once it's terminated, how can we reuse it?
Instead of terminating when you're done evaluating an X expression, you wait for another X expression.
So we have right now a thread with a single run method, right? Or a runnable with a single run method. Somehow we need two runs, two kind of runs. One that is my current S expression to be evaluated, and one is my run known to the thread. And so we have two kinds of runs. One run is running in a loop, which is kind of what you guys are saying. And that loops through and executes this temporary run one by one. Okay, so there's a temporary runnable around, and the long-lived runnable around, and the long-lived runnable iterates through temporary runnables. And the long-lived runnable has assigned to it a temporary runnable. So the long-lived runnable is just this unaware of the exact computation, and the actual exact computation to be done is done by the dynamic runnable. Okay, so kind of getting it? That there are two kinds of runs to be done. One is a long-lived run that goes through a loop, and the long-lived run goes and executes the current short-term dynamic run. Okay? And after each assignment of a new dynamic run, it goes and it goes and executes that, and then waits for the next dynamic run to be assigned. So we've got weights, we've got a lot of complicated stuff going on here. Okay? But that's the basic idea. Okay. So let's see how that materializes. So given that we've gone through this depth, we've got the basic concepts. What will happen to my evaluate parallel with helper class? This is the evaluate parallel with the runnable. How will this code now change? You guys have already said we need an object called thread pool. Okay? How many thread pools do we need, by the way, in our one? So the thread pool is a singleton. Okay? So I've got to go and use a thread pool singleton dot get, and I want to invoke some method on it. What method should I invoke on it? What should I do? What should I do to this piece of code? Let's put it this way. How should this change? This creates a thread. So this is my evaluate parallel with helper class. It creates a thread and it creates a joiner. You guys have already gone to this thread pool. So let me ask a more basic question to sort of motivate what I want to say next. I'm saying that this evaluate parallel with helper class cannot create a thread and cannot assign a thread to a local variable and cannot assign the joiner to a local variable if we are to reuse these objects. Why? So I'm trying to just, maybe I'm saying things you guys already figured out, but I want to go in slow motion. So the joiner and the thread objects that we have created are local variables. They're not stored in any instance variable. I'm saying if you assign these to local variables, so I'm just trying to say that thread creation cannot fundamentally occur. It can occur here, but it can't be assigned to local variables in this method if we are to reuse threads and joiners. I mean, and the answer is not very subtle. I just want to get it out from you so that it's, yeah.
Do you mean like that needs to be, the thread creation needs to be a part of the pool data type?
I want to motivate that next.
Okay.
But I want to first just say that I cannot assign a thread. If I need a thread here and I need to create a new thread here, assuming the thread pool is full, and I need to create a new thread, that thread creation can occur here, but that thread can't be assigned to a local variable. Similarly, the joiner cannot be assigned to a local variable because we want reuse. We want reuse between different invocations of evaluate parallel with helper class, right? We want one invocation to be able to reuse things created by another invocation. So this is not too subtle. I just wanted to sort of, and maybe I didn't ask the question in a proper way. So fundamentally, I cannot assign these guys to local variables because another invocation will not be able to get a reference to them. Okay, those two objects will be garbage collected, as you guys were hinting. So I have to go and store them in some global variable. I'm trying to go gently to the idea of thread pool, which you guys have seen before. So if you want to do that, assign it to global variables. We can do that in this class, in this particular method. But then we can, so let's go and say, so these two things, I should have maybe gone gradually here. Local variables of expression evaluated invocation cannot be used by another invocation of it. So we have to store them in global lists. We can do that in this piece of code, but for separation of concerns, let's go to another method, another class, and we'll call that the thread pool. Okay, that's the way to think about thread pools. Okay, we could have done this, we could have reused in a less elegant way, but thread pool gives us a more elegant way to do reuse. Okay. So the name of class and its methods and how to change this class. So how do we change this code to a new piece of code that uses a thread pool, and what should we name that class? Well, we already figured out that's called thread pool. Okay. And where I go and say new thread, with this X expression, what would I do now? Now that we know we want a thread pool, let's go and figure out what the methods of thread pool would be.
I think you already said it would be thread pool.get.
Okay, threadpool.get will give you the instance. Threadpool singleton.get will give you the thread pool instance. Now I want to go and so now what do I do? You're along the right line. So you want to execute something on the thread pool. And what do you, but I know what I want to execute, right? I've got these n expressions, n plus 1 expressions to evaluate. One of them will be done by the calling thread. The other will be done by new threads. So what do I want to tell, how do I want to tell the thread pool what to execute? I mean, there's many ways, so I'm not saying there's one way to do it, but just think of how this might go. We know how to tell a thread what to execute. We give it a runnable. Okay, so you're going too fast. So a single thread, I go and say, here's my runnable, right? And the thread will not, then I have to give it a joiner also. Okay? Now your thread pool, I give it, what do I do exactly? A runnable, but I've got so many runnables to do. No, but I want to do them parallel. I'm getting the obvious things out in gently. So I give it an array, and to this guy I gave it a joiner. Do I need to give it a joiner, or could I do better? No, why not, Mac? So do I give the thread pool a joiner, or I just give it an array? Could the thread pool itself create a joiner and hide the stuff from me? Right? Because I'm working at a high level of abstraction now. I just know what I want. I want these runnable. I know what has to be evaluated. How is not my business. I've got these runnables. I know these expressions. I create runnables out of them. And I just pass these runnables to the thread pool. And thread pool says, okay, one of these thread pools I will execute in your thread. The other runnables, I will go and find threads and bind them to the runnable. Okay, so let's go and see how that will go. I've got this is what I had. With the pool-based thing, I would go and say runnables I. We know we want to go and create a runnable, okay? So let's say we still want the same interface. Now what we do is we take each runnable and assign it to an element of an array, which is exactly what was mentioned before. And I will go and say threadpool singleton.get do parallel runnables. Okay. So the separation of concerns. The thread pool user creates the runnables. It knows, that runnable has to take these 3 arguments or 4 arguments. Okay, and that runnable will go and do the expression evaluation. It knows how to do that. And the thread pool doesn't know what these runnables do. It just knows there's a list of runnables that have been run in parallel, and it will handle them.
The constructor to S expression evaluator, where's joiner coming from?
Oh, sorry. So this was supposed to. This is supposed to no longer have the joiner. Okay, thank you. Good. Okay, so the joiner we take out. Good. Okay. Questions? Anybody done OMP? So this kind of construct actually occurs in many languages. Do parallel is something that we'll see exactly mirrored in languages and libraries. Okay, so this is the construct. Okay, I need to spell this correctly on the left here. So execute each runnable in a separate thread and wait for them to finish. That's what this call is. Okay, it's a blocking call, and it says block me till these have been done in separate threads. Whether you create new threads or reuse threads, that's not my business. Just do it. Okay? Questions? So invoker, unaware of threads and joiners, even though I have this joiner here, it's supposed to be unaware. Okay? And many parallel languages provide this construct. Questions so far? So I have, what do we have? We have the thread that's given to us. We have runnable. And we have joiner interface, and we're assuming there's a joiner, basic joiner class. Okay? And we'll also add to do parallel a quit method, which allows us to sort of just quit. You know, when we're quitting, we want some cleanup to be done. Okay? And there's a third method. You see the space here? There's a third method that Andrew has put in for efficiency, which I'm not going to show in the pseudocode. And we were still discussing it this morning whether we need it. So I'll go and I won't mention it right now, but in the assignment I'll give you guys an option of being a little bit more efficient with another method. Okay. And now let's go and look at what data structures we need. So we need to have some kind of collection, stack, queue, whatever, of joiners and workers. Okay? And the question is, what elements do we put in there? And the intuitive thing is that the intuitive thing is that my worker queue is a queue of threads. I copied and pasted there. So the intuitive thing is that the worker queue is the queue of threads, and the joiner queue is a queue of joiners. And I'm going to argue that's wrong. So first, let's go and see why the joiner queue cannot be a queue of the joiners as I've defined joiner here. That's the intuitive thing. My joiner has got a constructor called basic joiner, if it's a basic joiner, finish and join. I'm saying this joiner is not something that I can queue directly. I want to reuse joiners. I want to reuse joiners to join after creating threads for different expressions. So far, for each expression, I created a special joiner, and this joiner worked for that. For every list, for given a list of expressions, I created a new joiner that worked. Now I want to use the same joiner for different lists of expressions. What is it about this joiner? And again, this answer is not too deep here. Yeah.
We have to be able to reset the full value.
We have to go and reset the count. Okay, so we need some kind of mutable joiner. Okay, and the thread as defined here cannot be reused for the reasons we just talked about. The thread is got one run method. There's no notion of a dynamic run and a static run. Okay, so we need to have something else, and there's two ways to go about doing that. So this runnable here that I get from do parallel cannot be just passed to the thread runnable, because we want to use the threads runnable to execute runnables of different runnables at different times. Okay, so so a thread executes a single runnable, not multiple runnables. So a reusable thread does not execute a do parallel runnable directly. Okay, that's a subtlety. And joiner works with a single count initialization, so cannot be reused. Okay. Good. Questions? Okay. We have 3 minutes left and a lot of subtle concepts, but it won't hurt to go and repeat them next time. So let's go through. So we're going to have our worker queue be a queue of thread pool worker. It's a new interface we define. And our joiner queue is going to be a queue of mutable joiner, which allows the count to be reset. Okay. So the tricky part now here is what is a thread pool worker? Okay, and my animations I didn't get right here. The first thing is that thread pool worker is a thread. That's one choice. And the second choice is the thread pool worker is a runnable. And if I'd done my animations right, I would have had thread pool worker is a runnable come first and then be overwritten by thread pool worker is a runnable. Okay? So what do you guys think between these two things? Should we make thread pool worker a thread, or is a thread or a thread pool worker is a runnable? Both can work. And Andrew and I debated over it, and actually Andrew convinced me about the right way. And who knows what the right way really is. So we need a thread pool worker to be something that has both a long-lived run and a short-lived run. Okay? As it turns out, both threads and runnables have run methods in them. So we could extend either of them. But what fundamentally do you think is a thread pool worker? Is it a thread or is it a runnable? Is it a special kind of, new kind of runnable, or is it a new kind of thread? Is it a new kind of runnable which has more than the run method, some other methods? Or is it a new kind of thread that has more than the threads methods that already exist? Okay. Fundamentally, what do you guys feel it should be? So think about a thread. Thread is a unit of concurrent execution. Runnable is a piece of code that the thread executes. Have we created a new kind of concurrent execution? It should be runnable. Because concurrent execution is something that has to do with the operating system, it has to do with scheduling. We haven't done that. All we've done is created a new kind of runnable. So even though in 401 I taught Andrew these principles, he was the one who retaught them back to me and said, no, it should be a runnable, should not be a thread. Even though I've been teaching operating systems and teaching how to, so he was right. Child is the father of man. So we have a mutable joiner is a joiner that allows count to be reset. Thread pool worker is a runnable. So thread is a system entity and a concurrent activity. So we are changing. So anyway, I'll just go through this again next time because we're out of time. But we'll start from here, and I'll correct my animations and slides. So what I will do at the end of today is add the assignment on how to do on doing threads without thread pools. That's the regular credit. I'll add that, and with thread pools will be extra credit, and that will have to come after Tuesday. Okay. Okay, so we started on concurrency last time, and that's a totally new dimension in terms of concepts. Same infrastructure, we've got the Lisp interpreter, but a totally new set of concepts. And we saw that our evaluation function in S-expressions originally was serial. And that means we went through a loop and went and evaluated each element of, so if given a list of expressions to evaluate, we evaluated those expressions in the order in which they appear in the list. Okay, and that was safe, because if the expression evaluation had side effects, then we knew in what order those side effects had to occur. So that was well defined. But functional languages functional programming at least doesn't have side effects, and functional programming and concurrency actually go together hand in hand. So when there's no side effects, you can go and actually evaluate a list in parallel. And we also saw that if we do want a deterministic program, we can copy the environment before evaluating the elements, and that way at least we get deterministic results. Okay, so that part we did last time. We are going to go and extend what we did with parallel evaluation in this lecture. So just to remind you where we were, so we started with evaluate. Then we did serial. Then we did evaluate parallel two different ways, with lambda expressions and with the helper class, runnable class. And here I'm showing you the code with the helper class. And the basic idea there was that given n expressions to evaluate, or n plus 1 here. We'll do one of them in the thread that's been asked to evaluate the list. And then we'll do the other n in threads that are forked by the thread that was asked to evaluate the list. Okay, so let's call the thread that was asked to evaluate a list the parent thread. So the parent thread, if it's given just one expression to evaluate, it'll evaluate that expression. If it's given n plus 1 expressions to evaluate, it'll evaluate one of those expressions and ensure that the other n expressions are evaluated by different threads. Okay, so we used the thread constructor there, and and for each list that we had to evaluate, we created new threads. Okay, that's what we did last time. And of course, there was synchronization needed here, that after the parent thread has evaluated its one expression, it can't return the result till the results from all the children have been received. Each child goes and adds the result to a different slot in an array, so that array has to be initialized, or list, either way. And so it needs to wait for all of them to finish. Okay, so we had this joiner object, and we assumed that worked as needed. I didn't quite give you the details of joiner in terms of how it's implemented, but the joiner had a join method that the parent called to wait for the threads to finish. And each thread, child thread that finished, went and called the finish method in the joiner method, in the joiner class, and that's how we got synchronization. Okay, so any questions so far? And a problem with that, and I guess I have some slides again to remind you of the problem, was that we had a new thread created for each expression to be evaluated. So if we have three lists to be evaluated serially, the user enters one S expression that involves evaluation of a list, then it enters another S expression that requires evaluation of the list. Now the user does want these expressions to be evaluated serially. Okay, so we don't want to do, in fact, the user is going to enter them serially, and we won't even have a chance of concurrency because the user will wait for the result and then enter the other one. So what happened was that when there was serial execution needed, we actually created new threads each time, and we didn't just reuse the threads that had already been created. Okay, and thread creation is an expensive operation. So we figured that we would go and create a thread pool abstraction. We are calling it a thread pool because lots of other people call it thread pools too. But we're going to do thread pools in a different way than what the thread pools in Java, for instance, how they work. Okay, and the thread pool that we are defining mirrors exactly what we see in some concurrent languages. Okay, and just they have syntax, and we are using method calls. So the basic idea is that you want to say do parallel this set of tasks, and you specify what the tasks are. You can specify them as a bunch of runnables. You can specify them as a bunch of constructs in a programming language. Okay, and the do parallel is what it does is it waits till all the actions that have to be done finish and unblocks at the end of it. Okay, that's what we're going to implement now. So this is a higher level abstraction. It could be implemented any way we feel like. But we would like to do it with thread pools where we reuse threads. So the idea of thread pool is that somehow there's a pool of workers. They finish one piece of work, and they don't quite terminate. They say, okay, I'll wait till there's more work to do. Okay. So the motivation for thread pools comes from this example. I've gone and evaluated two lists. I'm a user, so I entered one list first, which in turn has two nested lists. That's on the left, and then I go and enter the same expression again. And with the method that we'd seen earlier, without thread pools, we would create 4 threads here and 4 threads here. So we'd have 8 threads overall. Okay, whereas we could do with just 4 threads. Okay? We could reuse the threads on the left for the right execution. Okay, so that was the motive for thread pools, where we just use T1 and T1, T12 and T2 and T21 on the left again for execution on the right. Okay, so that's what we want. And the question is, how do we get this? And this is an interesting problem from 2 points of view. Firstly, it's telling us how to implement something that occurs in a lot of concurrent languages. And more interestingly, it will require us to exercise in a fair amount of depth these constructs that we have seen before, which are easy to understand but hard to use. Okay, so the synchronized access, which really means that we want to make sure that some data structure that is to be manipulated by multiple threads is changed atomically. That means 2 threads don't go and change it at the same time. One thread that has to go and make a change finishes that change before another thread goes and makes a change, because otherwise we might have inconsistent results where you're in the middle of changing some things. Okay, you're in the middle of changing an array, and you've got added the element, but you haven't updated the index that points to the last element. So we don't want one thing to be done without the other. So that's why we want them to be done together atomically without interference. So the synchronized methods allow you to do that. Okay, we saw what they meant last time, and I've just reproduced the slide from there. And synchronized methods provide a coarse-grained synchronization. That means the whole method is executed atomically. Sometimes you might want some portion of a method to be executed atomically, and you're too lazy to go and make that portion into another method, or that portion may not be a logical piece of work. That rarely happens. Let's just say you're too lazy to go and make that piece of work in the method to be an independent method. So you can just go and say, put synchronized and some object, often it's this, and enclose that piece of code in curly braces after that, and that's a synchronized block. Okay, so you can have finer grained synchronization than method synchronization, and we'll use that in our algorithm. Okay, so I'm just reminding you what we have. And also in the previous slides we saw wait and notify. I didn't highlight them. So not all synchronization involves executing synchronized methods or synchronized blocks. That's just to make sure we don't tread on each other's toes. Sometimes a thread has to wait for the actions of another thread to finish. And so it's not that we are making sure that 2 people don't interfere with each other. No, these 2 threads have to cooperate with each other, depend on each other. So that's a wait and notify. Okay, so if a thread is waiting on an object, then a notify on that object will release that thread if it's the first thread in the queue. And you can have multiple threads in the queue too. So again, these constructs are not hard to use, not hard to understand, not too hard to understand, and not too hard to implement, but they're pretty difficult to use. Okay, most of the bugs that we see, a lot of the bugs we see in programs have to do with concurrency. Okay, yeah.
So for example, like the list example with the nested lists, with the 4 different, with the combined 4 different arguments of the inner lists, be running at the same time, would they have any sort of weights between them?
So the weights are in the joiner, in the magic joiner we had, right? Okay. So there was a list with 2 nested lists. So there's a join. So each list has 2 expressions being evaluated in parallel. So we have a tree of threads there, and the parent node waits for the children nodes to finish. As it turns out, we had at the top level 1 parent node waiting for two children to finish. Actually, since they were all expressions with 2 arguments, we had the parent thread waiting for 1 child thread to finish. But in general, there can be multiple threads required to finish. So in that join were notifies and waits. In the joiner method, in joiner class. And they use different joiner objects. Okay, so the top level one used 1 joiner object, then there were 2 inner lists, and each inner list had its own joiner object.
So they're just waiting for the one above it, basically.
The parent waits for the child. The child doesn't wait for the parent, right? The child does its work, doesn't even know about other children. The parent does its work, and before it goes and releases results, it goes and waits for the children. And that's done through the join. And actually, I didn't tell you exactly how joiner is implemented. So if you want to understand how it's implemented, try to understand the example I will go through today in class to show the synchronization. But yes, that was the synchronization. Okay. There were no other data structures, I believe, that required a critical atomic access. So, so we don't have to worry about that aspect. But now we'll have to worry about data structures that have to be locked. Okay. But I'm just so this is the joiner that we had, and the semantics was that the join method blocks. Okay, so given that the basic joiner, the constructor took an argument. So let's say that we created a joiner with constructor argument n. Okay, and then when we did join, the join waited until what? What are the semantics? I didn't tell you the implementation. What are the semantics of the joiner? So given that the count is n, the join would go and wait until? What's the relation between join and finished? How many finishes? And finishes. Okay. The tricky part there is that the finish calls may occur before the join method is called, and vice versa. So that is, it's clear that one of those methods has a notifier, one of these methods has a join, has a wait, but we have to make sure that if the join comes early, it doesn't just unblock or it doesn't block forever, and that's a tricky part. Okay, and we are going to deal with such trickiness in the thread pool implementation also. Okay, so constructor initializes a count, and join blocks joiner count number of finish calls have until made by finishes. So let's go back now to our do parallel and see how we can implement it. Okay, and we saw some of the big decisions that we had to make in implementing it last time. I'll just go through them. Before we do that, let's go and sort of figure out what goals we have. Okay, and depending on the goals, we can come up with many implementations. And given, of course, a set of goals, again, we can come up with multiple implementations. So what you will see here is one way to implement the goals. So these seem like motherhoods, obvious things to do. But not all thread pools are implemented to obey these goals. So we do not want to create a thread unless it's needed. Okay, so even if we have eager evaluation and our user only enters this with one expression, we shouldn't create more than the thread that was created by Java, the main thread. Okay, so that implies in multi-operand if no multi-operand expression is input, do not create a thread. That's what I meant to say here. Now, we can say that, we'll do some parallel evaluation. We'll create, but we won't create maximum concurrency. So what we're going to instead, so that's a fine goal to have. Okay, every decision we make has trade-offs. Here, what we'll do is we'll make sure that, given a list, we use maximum concurrency to go and evaluate it. By which I mean that every component of the list should be evaluated by a separate thread. Okay, that's our goal. But this doesn't mean that these threads will execute concurrently on processors. Okay, processors, they aren't infinite number of processors. We can create arbitrary large lists that have to be evaluated in parallel, but we can't just dynamically create processors on a computer. So the operating system or the underlying language might actually go and map your threads into multiple threads into one processor, and that we won't worry about. There are some algorithms that get into that are heavy on performance that go and try to figure out how many processors there are, assume that they are the only application running on that computer, and go and create the exact number of threads that are needed, that can be run those processors. Okay, we won't assume that we have a dedicated computer, so that part we won't optimize. And by the way, in Java, there is a call you can make to figure out how many processors there are on the computer. So we'll try to minimize the time a thread is idle. Okay, that means not doing work. If you've studied operating systems, a thread can be ready or current. When you have multiple threads mapped to a processor, for those of you who haven't done operating systems, can you try to figure out what the difference between a ready and a running thread is? What does the English word ready and run convey to you?
One thread is waiting for something to run, and then the other one is just, or a ready thread is waiting for like an input to run, and then a running thread is processing an input, I would imagine.
So the running thread is processing.
Yeah, it's processing something.
So you're saying when a thread waits for some action to occur in another thread, that waiting thread is ready, and the thread that will unblock so if thread T1 is waiting for some action to occur, and thread T2 is the one that will notify it and make it make the wait unblock, then the first thread is ready and the second thread is running. Is that your intuition? Okay, so that's a good intuition to have, but that's really, the first thread is really waiting. Okay, so the first thread is waiting, and the second thread will make it unwait or unblock. But I purposely said when you have multiple threads that can execute on a single processor, what is the distinction between ready and so what you were thinking of as ready is a started thread. Okay, the thread has been started, it exists in the system, but it's waiting. Okay, it could be waiting on a wait call, it could be waiting on input. Oh, that's what you meant also about input, right? Yeah, it could be waiting on input. And the second thread is the one that's going to unblock it. So it might, get the input and give it to it, or it might just go and say notify. So that is blocked versus not blocked thread, okay? Or we can say waiting versus non-waiting thread. But I'm talking of ready versus running, and maybe the jargon that operating system people use is not quite intuitive. But somebody else want to try? Okay.
Is the ready thread always dependent on other threads?
It's dependent on other threads. That what Andrew said had to do with dependency. That there was one thread that was depending on another thread. So what do you think happens when there are 3 threads and only one processor to execute? What do you think happens? What do you think the system does?
Puts them in the ready state and runs the running one.
So it goes and puts them in a queue, right? If there are 4 of you who raise your hands, I can only allow one of you to run or to actually ask the question. So you're in a queue, and maybe if the question has to be answered by every one of you, I'll go and pick you guys in some order. So if you are not blocked, okay, if you're not blocked and you're eligible to run, but you just can't run because you raised your hand, you're ready, okay? Somebody who hasn't raised their hand is blocked, okay? They're thinking or not bothering, okay? So, but if you raised your hand, you're ready, and the one who's actually answering is the one that's running, okay? So that's an important concept. And we want to make sure that minimize the time is idle and not available for, so we want to minimize that time, okay? And so we do want to make sure, we can't go and eliminate that time because a thread may be ready to work, but it may not be scheduled. So we have no control over that. So you want to minimize the time that a thread is not ready to do work. Okay? And those of you who've done web programming where there's not much synchronization, somehow I've seen this in newer generations. People tend to use sleep a lot. Okay, we'll just sleep. It has to do with the fact that this HTTP server is stateless and it can't invoke callbacks in your client. So if you want to know whether the server has done something, you keep asking it again and again. Have you done it? Have you done it? Have you done it? Because it can't go and assume a persistent connection and call back. Okay, so that's the kind of programming that web programming has encouraged. But we aren't in that situation. We are assuming that there can be coordination between the different components. So no sleep. Okay, and like I said, I see the younger generation, including Andrew, use sleep a lot when we don't need to. Okay, and we also want to make sure that we don't want to block a region for We don't want to lock a region unnecessarily. Okay, so if there's one piece of code that calls four different pieces of code, and only two of them need synchronized access, then we shouldn't go and put it. We shouldn't go and synchronize the access to the pieces that don't need synchronization. Okay, so we want to minimize at the time a thread is waiting. Okay, so with these goals, things become more challenging. Okay. Questions? So we saw what the thread pool might do. We know that we've got a do parallel construct, and it takes a list of runnables. Okay, and in Java you can say runnable array, or we can say runnable dot dot dot. And runnable dot 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 means that you don't have to construct the array when passing, calling the method. You can just go and enter the elements one by one, and this has to be the last argument. Okay, and we know that we're going to reuse. We're going to reuse not only threads, we're going to also reuse the joiner objects. Okay, we don't want to allocate objects again and again unnecessarily and rely on the garbage collector. So we will go and reuse a joiner object after it has been joined, successfully joined. Okay, so that means we need to have a queue or a list. We're just going to use a queue, but we need some kind of collection, list of available joiner objects and a list of available thread pool workers. Okay, so we have a thread pool, we have a bunch of workers, the workers are going to be reused, and we want to have a list of the ones that are available for the next use. Okay, so that part we got. Since we want to reuse the joiner object, we don't make it an immutable joiner object that has a constructor that sets the count forever. We're going to have a mutable joiner that allows this count to be changed once a finish call has been successfully executed on it. So things are becoming more complicated. Okay, and one issue that we had was that what is the thread pool worker? And we can say the thread pool worker is a thread. Okay, and we said no, thread is something that's provided by the underlying system. We're just trying to use the system in a different way. We're not changing the nature of a thread. And so, inheritance is one of these things also. It's not too hard to understand, but how to use it is tricky. And we said what we'll do is we'll make the thread pool worker to be runnable. Okay. So now we have two kinds of runnables. One runnable that is passed to the thread object, and as far as the thread object is concerned, that is the runnable. So when it starts, it goes and executes that runnable. Okay. And that runnable in turn is associated with a dynamic runnable. So that runnable doesn't know what really to do. It looks for it's an object, and it looks for a dynamic runnable object that can be changed dynamically to determine what is the next piece of work it should do. Okay? So that's what and we'll see exactly what this means later, but that's the intuition, that we have this runnable from the point of view of the thread, and then that runnable is the persistent runnable. We don't want it to finish. That means it should be going around in a loop. Okay? And in each iteration of the loop, it goes and executes the next dynamic runnable that has been set in it. Okay? So you guys get the basic idea so far? Questions? Okay, we're going to flesh it out. Okay? So let's have this fleshing out here. I have a thread pool worker, which is a runnable. Okay, that's what these purple lines mean. The dashed lines mean has a. Okay. We have a mutable joiner that is a joiner. It overrides, it adds some additional methods, and that additional method is set num threads. So we can set the number of threads dynamically. We don't have to rely on the constructor. Okay. And we have a thread pool that has references to a bunch of thread pool workers and a bunch of mutable joiners. Okay, so far so good. The thread pool worker knows about the thread pool. Okay, so we have a constructor there. So that all makes sense. Can you guys think of, those of you who are really alert, any other methods I might need in my thread pool worker and thread pool? So I say the thread pool worker is the thread pool worker is the one that is a runnable, and that runnable is the one that's passed to the thread object. As far as it's concerned, that is the thread. That is the runnable. That's what it's going to execute. But we said that that's going to go around in a loop, right? And what's it going to do in each iteration of the loop? I just said it, 3 minutes earlier. So we want a reusable runnable, right? So what is it going to do in each iteration of the loop again? Wait, and then that's good. And then after the wait unblocks, do what? Run what? It itself is a run method. Thread is going to run it. See, this is why concurrency is hard. We want it reused. So it's the worker. So it has to be given work. So somehow it should be given the next piece of work. That work changes dynamically. So call the pool to, or so it needs a piece of work somehow. It needs to know what the next piece of work is. So it's somewhere here we should have a way of getting the next piece of work. So it's going to go through a loop. It's going to wait for the next piece of work, and it's got to know then what the next piece of work is. Right? So we need some way to do that, and what might be in terms of what methods that yeah, a piece of work, yeah. So we are not trying to do that level of optimization. We are saying that given a list, we are going to evaluate all elements of the list in parallel. Okay, and we can just fork off a bunch of threads that will do, and we're not going to figure out which takes small amount of work, which takes a large amount of work. So there's no greediness involved here. So there's a bunch of expressions that have to be evaluated. Okay, originally what we did was, let me remind you guys, that each piece of work was runnable. Okay, so this is the thing. Do parallel is given a bunch of runnables to execute. That's a piece of work. Okay, in a programming language, that might be a construct. This runnable is not what we pass to this thread. That is what our first solution did. Our first solution just took the runnable that we were given in do parallel, or I mean, it was not do parallel, it was evaluate the list. And it went and told the thread, here is the runnable, and the thread went and finished that work and terminated. We don't want that to happen. So we're going to pass to this thread this guy, a thread pool worker, which is a runnable that can somehow go and execute runnables of different do parallel constructs. Okay, so a do parallel is called in one serial execution, then a do parallel is called another serial execution. And this basic thread pool worker should be in its run method, should be able to switch between the runnable passed to one do parallel and the runnable passed to another do parallel. That is the key. Okay? So somehow it needs to know, in each iteration of the loop, it needs to know what is my current runnable to execute. Sorry? So it needs a queue, maybe it needs a queue, or so it can pick it up from the queue from the thread pool. Okay, that's one way to do it. Okay, and that's indeed that's a good way to do it. Except that we have these joiner objects also, so it needs to also call a finished on a joiner. So one is that it can pull things from a queue, and the opposite of pull is, so for push that would mean somebody goes and says, here's your dynamic runnable. And not only that, here's the joiner object too. So each time doParallel is called, doParallel goes and says, somehow finds the thread pool worker and then creates a joiner object or finds a joiner object for that task, because it's got to join later to those tasks. So it goes and finds a joiner object and finds a thread pool worker and says, here's your runnable, here's your dynamic runnable, and here's the joiner object that you should refer to after you've done your work. Okay? That's the push approach. The pull approach is a little bit more complicated because you've got to coordinate the joiner object and the runnables together. Not every runnable is associated with any joiner object, so that gets trickier, but that is possible to implement. You may want to think about how to implement it. Okay? And then we're going to have some other methods. Who knows why we need them? But has the thread pool, has it started, and we'll see what that means later. So the thread pool worker is a runnable from the point of view of the thread and has a runnable because it has a reference to the dynamic runnable that it should execute next in its loop. Okay? Questions? We'll have this finished method too, just in case we need it, that once the thread pool worker has completed work, it can call the finish method in the thread pool. Okay? We'll have a quit method in the thread pool that goes and says, just quit, we're about to quit, clean up, and terminate all the threads. And how would you terminate a thread, by the way? If you were the API designer of, how might you terminate a thread? There's two ways to do it. So if you're an OS implementer, you can think about how to implement the kill method in it. Okay, so you kill a thread. But supposing the operating system did not provide the kill operation. Kill operations are very dangerous. Okay, Java won't even let you go and invoke them in a lot of contexts. How can we make sure that the thread finishes execution?
So when it's waiting for a new task, you have it before it starts that new task. So it waits for the signal that it will do its thing. Then it checks a variable to see if the variable will change to kill or not kill. Which really it's like look for more tasks or stop looking for tasks.
So remember, exactly. Remember, when you do a thread.start, what that does is it says, who's my runnable? And let me go and execute the run method of it. That run method, we know in our case, is going to have a loop. And that loop, before it goes to the next iteration, can check some variable, whether it has been set or not. If the variable has been set, it'll go and terminate. And that's much better than just killing a thread. Can you guys think why killing a thread is a dangerous operation? That you just unceremoniously, I mean, killing is just not a good operation in general, right? But you just unceremoniously go and say, hey, kill thread. And that is a problem when it's in the middle of doing something. Can you imagine it being in the middle of something and you say kill it and that causes repercussions on other threads? Yeah. It's in the middle. It's got a lock. Okay, it's got the secret that you want to know, and it doesn't release the lock, and other threads just have to wait forever then. Okay, so that is why you don't want that to happen. Okay, and even if you can detect that and release the, it's not clear. The system could detect the fact that it's killed and release the lock, but it's not sure that the lock should really be released because the data might be in an inconsistent state. So you want to make sure that the thread goes and puts the data in a consistent state before it releases the lock. And that's why the systems don't, just don't release the lock on their own. Okay, good, excellent. Okay, so we'll have a kill method in the thread pool worker that will go and set the Boolean. Okay, so we know a little bit about what we want to implement by these external methods. Okay, questions so far? So let's go and see how our do parallel works. Okay, well, why don't you guys tell me, now that we've understood so much. So tell me, what are the steps that this do parallel should do? Just in any order. It's been given a bunch of runnables, yeah. Okay, slowly. What is the first thing you said? Okay, so what if we are, let's consider the case that this is the first do parallel ever being executed. So there is no first. The thread pool work, I have an empty queue of thread pool workers. Sorry, a little louder. If full. No, I still don't understand what you're saying. Okay, you need a for loop, yeah. So we've got n runnables to execute, and the first situation is that this is the first do parallel. So in a loop, do what? Okay, Andrew's got his hand up. Yeah.
You would have to check how many threads are currently active first, and if there aren't enough, then you make new threads.
Okay, so we create. So that's the more general case, that we go and see how many runnables we have. If we have n runnables and m thread pool workers we have already created, then we need n minus m more workers. Right? So that's the part we do in a loop. Okay, and that's one. So that's a pool. That's a pool of thread pool workers. And what other kind of object does it keep a list of? Joiners. Same thing with joiners. Goes and says, hey, do I have enough joiners? Do I have I allocated? Do I have another joiner? If I don't, create a new joiner. Okay. Okay, so that's good. Those are two steps. What else should we do here?
We then have to check to see if, like, how many of those runnables in the pool, like, if you have any, are actually running.
Okay, let's okay. So we have to determine how many thread pool workers there are. Now, what does that really mean? That meant how many thread pool workers are free, or how many thread pool workers have created?
I was thinking created first.
So let's assume free. Okay, let's assume that we have lists of all the free ones. Okay. So whenever you use one, we remove from the list, and whenever it finishes work, we'll go and put it back in the list. Similarly with the joiner object. Okay, so now I needed n runnables. I found m free ones in my list. I allocated n minus m. So now I have n runnables. I have one joiner. What should I do with these two objects? I've got n runnables and I've got a joiner object. What I found them. What do I do with them? What do I do with the n runnables I've got? The n thread pool workers. Call this set dynamic runnable. Okay, and what do I do with the joiner? Sorry. To the good, exactly. Pass it as an argument to the set dynamic runnable, and then what else do I need to do with it? So that makes sure that those guys can call the finish method on it. What else does the master? What else does this yeah?
You have to set the number of runnables that you have to wait for.
Okay, so in the joiner object, I'll go and set the. I hope I've got that code, by the way. I think I might have forgotten that. Set the number to be n, and then what if there were n plus 1 runnables? How many thread pool workers do I find? What did we say? N plus 1 or n? N. So I have to do my work also. I have to go and pick one of those pieces of work and do it myself. And then after that piece of work, do I return or do I wait? I join. Okay? So let's see. I have to do something from 1 to runnables length minus 1. Okay, because I'm going to, if this n plus 1, I'm going to only ask for n. I'm going to get or create worker. Assume there's a magic routine that does that. Okay? Let's assign that to an array. Who knows whether we need the array or not? And I go and set dynamical runnables joiner. And that means I need a joiner object. And I go and say, I go and take the 0th runnable and run it myself. So I need to go and get a joiner object. And I did set the number of threads to the correct one. Okay. And I do joiner.join. Right. So at this point, we have computed the function. Any other steps I should do after this? When join finishes, all the runnables have been executed, and we have the results we have the results we need. What should I do with the joiner object and the thread pool workers? So what's the opposite of get or create joiner or get or create worker? So get or create worker went and took something out from a list and gave it to you. Now these workers are free. What should I do? Return the joiner, return the workers. Anything missing here? Okay. Seems fine. Now, let's talk of efficiency. Let's talk of goals. We said a thread should not be idle should be idle for the minimum amount of time it needs to. It should never be idle. Have we created? Does this situation allow threads that are ready to workers that are allowed ready to work to not get the work, to not be eligible for work? And this goes back to Nathan's comment about greedy algorithm and some expressions taking longer to evaluate than others.
It's the idea of taking and returning workers to a pool after they're all done. If one finishes early, it's not returning to the pool.
So when we went and joined, we waited for all n of them to finish. When all n finished, then all n will return to the pool, even though one of them might have finished earlier than the other. Okay, see that? So I think that's what I have here. So, before we go to that, let's assume this works. I forgot about synchronization. What kind of synchronization do we need here? So let's say T1 is the thread, that's the parent thread that goes and executes this piece of code. Can any other thread execute this piece of code simultaneously with T1? Do we have to worry about synchronizing any of these accesses? So you mean protected by synchronized by a synchronized? But we should do that only. You don't mean protected as in Java sense, right? Like public protected. These are all public methods here. Okay. But what I'm saying is that can multiple threads execute this piece of code at the same time? Yeah.
I feel like they can't, because then you could just accidentally assign like the same joiner or worker to a different task.
So I'm the parent task. Let's say I'm the first. I'm T1. I created T11, and I created T12. Can T11 also execute this piece of code? The child? T1 executes it whenever it has a list of expressions to evaluate. T11 is the child thread. Is a child thread. Can it also be a parent thread? It can have another list to evaluate. What's that going to do? It's going to go to the thread pool singleton dot get instance do parallel. So we might actually have T11 also going to execute the same piece of code.
How do you protect it if, like, say you have the two children who are also both parents trying to access the same workers and the same joiners at the same time?
So the things to be protected. So we've established that these two threads can execute this piece of code at the same time. And then the question is, can they interfere with each other? And you just hinted as to what the interference might be. Because there's one list of joiners, there's one list of thread pool workers, and we want to make sure that these lists are accessed atomically. Okay? So we do need protection, not protection in terms of access control, but protection in terms of concurrency. And we can just go and put a lock on the whole method, do parallel. And Robert doesn't like that. Why don't you like that?
Because T11 will never join. They'll never finish. So you just join forever.
So when you go and put this lock here, the child process will never get a chance to enter this piece of code. This is the problem I was telling you about, that we don't want to lock something larger than what we need to lock. Okay? So this is the kind of, like I told you, figuring out how synchronized keyword works is not hard. Figuring how to use it is difficult. Okay? So we don't want to put a lock there. Forking child blocked by forking parent. Okay? If the child also needs to fork, it is blocked by the forking parent. Okay? So we don't want this, and what we want is individual locks. So we can go and, I don't know whether I put so I don't think I put all the locks that we need, but here are some examples of the fine-grained locks we need. Okay? So this lock, we want to make sure that get or create worker and return worker mutually exclude each other. That will, yeah.
So just be sure, we would use synchronize and like getter create worker. Like for that method, it would be a synchronized method.
So getter create worker would be a synchronized method. Or you can, if you want, you can say synchronize this on this, but I would rather make getter create worker a synchronized method, a return worker to be also, you can make return worker a synchronized method. That's what I would have done, but what Andrew said was, hey, why do we want to call synchronize again and again? Let's go and just do synchronize this on the whole loop there. That way we don't have to do it multiple times. Okay, they both will work.
But if you call it never in the context, then you have to remember that.
Yes. So yeah. So this becomes finer grained thing that, you know, what if your return worker is called from somewhere else? Okay. So you can go both ways. But the point is that this piece of code should be synchronized. Okay. As it happens in this particular program, this is the only place it's called from. Okay. So that's why it kind of works. But actually, I'm going to argue against this whole loop completely. Okay. Because it is the earlier worker has to wait also. Okay. So I don't think I didn't put a lock here. We should have a lock here also, and we should have a lock here also. And I think I just forgot or didn't put locks there. Okay, now let's go and handle the situation about early worker idle. Okay, so the early worker is idle. And can you guys imagine how we could do things differently to make sure that the early worker is not idle while using the same structure? We don't want to change everything. So a worker, when it finishes work, it goes and calls a finish method in the joiner, right? We don't want to change the joiner object. So what else can we do at that point? The worker knows it's finished. The parent doesn't know it's finished. The parent only gets to know all workers are finished because it's calling the join method. So we have to do something whenever a worker finishes. Okay? And so we don't want to do this. And I told you guys that, look, ThreadPool has a finished method in it. So the worker calls the finish method in not only the joiner, but also the ThreadPool, and says, hey, I'm finished. And at that point, we can go and call return worker there, so that the worker is released immediately and doesn't have to wait for its fellow siblings to also finish work.
So it just returns itself.
Yes. But we are putting the ThreadPool worker in the ThreadPool object. So who executes this thread? This piece of code is executed by tParent and also by a forking child. And which thread will go and execute this? So let's say T1 fork T11 and T12 and T13. Will T1 execute this, or will T11 and T12 execute this? Children. Okay, so it'll be the children executing method in the parent. Okay. And so now there's even more reason to go and protect the data structures. Okay. Now you believe that concurrency is difficult? The good thing about this is that this is a small piece of code that has short answers and long amount of thinking. Perfect for an exam. Okay. So there's, it's tricky, but it can be reasoned out. Okay. So those of you who have been very quiet, hopefully you've been paying attention and understanding, and you'll need to recreate this whole logic again in your head later. Okay, and this was the easy synchronization. We're going to get to a little harder synchronization in the next slide. Okay. So part of the challenge here was coming up with the API. So coming up with the API and get the synchronization at the same time is difficult. Okay, but given an API, the synchronization should be easier, and that's the kind of stuff you have to do with the joiner object. Okay, questions? Okay. So I'm not quite sure what you mean by that. You're the guy who said that we have to call dynamic runnable. What more do you want?
Where is this function called?
What function?
This threadpool.finish.
It is in ThreadPool. Sorry, when I go and say this, this is bad nomenclature. I mean, the finish method is in the ThreadPool object class. That's what I mean. It's not a call. The finish method is in ThreadPool and the do parallel is in the ThreadPool. That's what this nomenclature means. This is pseudocode.
Right, I think he's asking who is the caller of threadpool.finish and where is it?
Who is the caller of ThreadPool.finished? Who do you think would be calling this? The So we haven't come to that. But whenever the child threads runnable finishes his work, it's going to call this. We haven't come. This is not all the whole code. But we know that the child thread has to call this. That we know. What piece of code init calls it, we'll just go in. But we know it's running in a loop. We know in that loop it goes and gets the next piece of work, does it, then goes and joins the joiner, and then goes and calls finished in the joiner, then calls finished here. I mean, that's what it'll do. Okay, but we'll see that exactly in the next slide.
So you synchronize the get and then create worker in the parent thread. You also synchronize.
Hang on. Synchronizations occur in objects, not in threads. Threads execute synchronized methods. They are declared in objects. And an object can have multiple methods. And that's why I'm going and showing you which threads can execute which method. So this method is executed by the parent thread. If the children never go and fork anything, they will never execute this method. Okay? This method will be executed by each child that's ever created. Whenever the child finishes its next piece of work, it will go and call this. So this is a ThreadPool object. ThreadPool object is not associated with any inherent thread. Any thread can go and call join in it. That's a parent thread. And then that can go and fork other threads that can go and execute methods in the same object too. Okay? Does that make sense? This is an object versus a thread. It's not as there's a one-to-one correspondence between objects and threads.
But you want to write the synchronize this, you need to put a statement in a curly bracket, right?
Okay, so if I go and put synchronized in the method header, it means the object in which this occurs. So we are synchronizing on the ThreadPool object. Because ThreadPool object has got the ThreadPool worker queue and the joiner queue. Similarly, this is very important, a very good question, that what are you synchronizing on? And all of these locks happen to be synchronizing on the ThreadPool object. Which there's a singleton, there's only one of these. Okay? Questions? No? Okay. But we haven't done all the methods. Okay? This should be ThreadPool worker.kill. And the W here should be capital, okay? But we've got the ThreadPool create new worker method to worry about. Okay, there's get or create new worker. We'll assume that the get from a queue is simple. We won't bother with that. So get or create new worker will go and either get it from the list or we'll create a new worker. So we look at the ThreadPool.create new worker. We know there's a ThreadPool worker has got a set dynamic runnable. We've got to figure out what that does. We know ThreadPool, so this is ThreadPool.quit. We know ThreadPool has a quit method, and we know ThreadPool worker has a kill method, okay? And we know that ThreadPool worker has a run method, okay? So these are things we know from the headers, and I've got a few mistakes that I pointed out, okay, which I hope I'll correct before I release the slides. So let's go and figure out what each of these methods does. Okay, So what are some easy methods here so again, I can give you guys the answer, and those of you who don't want to think, you'll be very happy. But there are some of you who want to think. So I'll try to go and teach to you guys. Okay. So those of you who are thinking here, tell me what are some of the steps that these methods have to do. I've got 5 methods here, so surely some of these things can be derived, what I've said already. We'll create, okay, so create new worker, what does that mean, create a new worker?
Making another thread to process the input.
So you're creating, this is where the new thread call is called. Good. Okay? Good. So that's one thing we know should happen. Okay? Yeah.
So would kill just abort the process the worker is doing and return it to the pool?
So kill is actually, I didn't go and say which class it is declared, and is declared in threadpool worker. So the threadpool worker kill will do what? Actually, Nathan already gave the answer a long time ago. How will we terminate the loop?
Create a variable to, or does it set a created variable to be done and then when it comes it checks that?
So the kill will just set the variable. Okay. And what will the threadpool.quit do then? That's the thread pool. Who will call the kill method in the thread pool worker? Yeah, and that would be the quit method. Okay. So the idea is that the thread pool, we call quit when there's no work to be done at that point. All the thread pool workers, we assume this. All the thread pool workers are in the queue at this point. They're not doing any piece of work at that point. And we'll go and just call kill there. So that's easy. What is the easiest method here, which we haven't even looked at so far? Sorry? Oh, that's the hardest one. So that leaves us only with the set dynamic runnable. Okay? So that's going to just go and initialize some variables, right? Okay. Again, I'll still not quite give you the details, make you guys exercise your thinking. So what will the run method do now? The easiest method or not the easiest method? We don't know. Just anything you can think of, yeah.
It will give the new thread or the thread worker the task it's going to run.
So the task is going to run is being yeah. So the ready state, I'm glad you guys are now going to the ready state idea. Ready state is something that the operating system figures out. So it just needs to know whether it needs to wait or not to wait, and that kind of, So when threadpool worker.run is executing, it is in the run state. It's guaranteed to be in the run state. Okay. So it's going to do what kind of things? What are the various steps it has to do? Look at the variables that are involved in this particular object. What are some of the instance variables here? Dynamic runnable is an instance variable. What other variables? Joiner is an instance variable. And there's one more variable that between first Nathan pointed out and then Chris pointed out, the kill variable. So let's go and see what it's going to do with all three variables.
Or if it's set be killed, then it won't do anything like kills stopping it from interfering with the blocks in the system.
So that's why we're not killing directly. So it's going to, so kill.
Variable active, then that halts any further processing.
Right, so how is it doing processing? It's doing, it executes a dynamic runnable, and then supposing it's not being killed, what does it do next after that? Looks for more, so it waits for more work. And it does that in a loop. So the killed variable is going to essentially determine,
Returns runs.
exit the loop. Okay? Okay, we've got the basic things. Anything else that I'm missing that you guys can think of? We'll think of those later as we fill up these things, but anything else? Okay. And let's go and see the various threads involved. I should ask this question too. So create new worker is in ThreadPool and it's created, it's done, supposing there's only one parent and there's one child, okay, T1 and T11. So the parent thread, the parent is going to actually say create new worker, okay, because it does the fork. Set dynamic runnable executed by the parent, quit by the parent, killed by the parent, right? Because threadpool worker.quit then calls threadpool.kill. Okay, so it's very important to kind of understand, given an object, what threads are going to execute the various methods of it. And threadpool worker.run is actually executed by the child, by the worker. Okay, so T11 here means the worker thread, and T1 means the parent that found the work, that gave it the next piece of work. Okay, so we need some synchronization. Okay, and that's something we have to worry about. So worker, we'll create a new threadpool worker, and we'll go and create a thread and associate that with the threadpool worker. So each threadpool worker is associated with a single thread in the operating system, one-to-one correspondence. Okay, we never keep track of the threads directly. We never store them anywhere else. Indirectly, we keep track of them through the runnables. Okay. The easiest method, the constructor, just initializes variables. Okay. The quit is also pretty easy. It goes through all the workers, assuming that all the workers have been released. That's an assumption made here. And it goes and calls kill in the work. What does kill do? Oh, I guess I have that later. We know the threadpool worker.run is going to go through a loop. Okay, so let's begin the loop. There's no condition here because we'll break out of the loop. Okay. What does it do? It goes and just says, what's my dynamic runnable? Let me go and run it. Right? So what should it do after the run? Access a joiner. So not join, call finished. Anything else it needs to do based on what we said earlier? Return the worker. So threadpool.finished. Actually, this should be this. Threadpool.finished this here. Okay. Anything else? I was so afraid of running out of slides today. You're on 15, I've got 29. Anything else? We need something to block on. We can't just keep going on and on, right? Because we'll execute the same dynamic runnable again and again and again and again if we just go through a loop like this. Right? So what should we block on? And what should what should unblock us? Which method here should unblock us? And we need the run method to block before it goes and executes run. And what method is going to be able to unblock it? So set dynamic runnable should go and unblock it, because it knows there's a new piece of work. And this guy, this should wait, this should do a wait and that should do a, okay? So any other synchronization needed?
Sorry, what do you say block?
Sorry?
What block?
So yeah, how do we block it, by the way? We need to block before we do this. What do we know? What do we have to block? The joiner block is not going to work here. So what should we do? What exactly should we do to block? So we know that this is the part where we have to block, and this is the part where we have to unblock. Okay. So what do we have in our arsenal to go and block and unblock? So we can wait on ourselves. We need an object to wait on. Why not just wait on this? And then this can notify this. Okay? And I don't have to do that. I can just do wait and notify. So here's the wait, and here's the notify. Okay? We've got the basic part here. We need a little bit more synchronization, so we'll do that next time. Okay. We've already done eager evaluation, as long as we are happy to create a new thread for each expression. And that taught us about eager evaluation, but that didn't teach us as much about concurrency as I'd like you guys to know, and as much information as you would like, you need to know if you want to build a really concurrent application in the real world. So here's the framework. We did separation of, there's a lot of separation of concerns now that we are reusing threads. That's the goal here. And the code that's doing eager evaluation figures out what expressions have to be evaluated, which expressions have to be evaluated, creates a bunch of runnables, which represent a piece of work that evaluates an expression. To each runnable, it gives the list of expressions to be evaluated, and the list in which the runnable should go and put its result back. Okay, that's the variable e and e eval here. And it also tells each runnable which element of the expression list to evaluate. Okay, and the runnable is going to basically evaluate that expression and store it at the appropriate index in the result. Okay, so it creates the runnables. That's something that's very specific to eager evaluation. And then it goes and uses this magic class, which is not so much magic, because we did see a lot of it last time, which is a thread pool. We have only one thread pool in the whole environment, in the Lisp environment. So we get its singleton, and we say do parallel, and it gives, and the do parallel is a high-level construct that gets a list of runnables. Okay, and this do parallel construct exists in many languages. Here we are going and representing the piece of work in a runnable object. In programming languages, the piece of work happens to be some syntactically enclosed, some syntactically defined construct. Okay, but conceptually, that it's the same thing in those languages. Okay, if we get time, I'll actually show you the exact constructs that some programming languages have had. Okay, so the question then was how to do parallel. Okay, and we are invoking this in an object of class threadPool or type threadPool. So let's go and look at this do parallel method. What does it do? What should it do? It's got to get the piece of work. It's got to go and iterate through the pieces of work. And we are going to go and give each piece of work to some worker, okay? And since we are a thread pool, we are not going to necessarily create a new worker each time. We are going to say, if there's an available worker, give me that worker, or create a worker, okay? And that worker is actually a dispatcher. So it has a piece of work that it does, which is just go through a loop looking for the work to be dispatched. So the runnable that we've got here is the work to be dispatched, and the worker is the one that's going to actually be dispatch that work. So its work is to dispatch work, okay, like a typical manager. So some magic happens, and each worker goes and executes its piece of work in a separate thread. Okay, we aren't concerned how that happens here. We know that if we have n expressions to evaluate, or n plus 1 expressions to evaluate, why should, we can do one of those expressions. So we create only n workers, or we find only n workers, and then one of those pieces of work we go and execute ourselves. Okay. So many languages that I've talked about, when their implementations actually create n plus 1 threads. I've actually looked at that, but we are going to be smarter and create n threads. Okay, that makes our code a little less clean. Okay. After doing the piece of work, we don't want to return till all pieces of work have been finished. Okay. So we are the thread. We've been told by somebody else who needs our value that please do all these pieces of work, and they are waiting for a result. So this particular do parallel has got to wait for all those workers to finish. Okay. That is what makes this whole exercise interesting, because we have to now coordinate among various threads, and that coordination requires, it can be tricky from what I've seen in the answers to questions and what I've seen in Piazza questions. So the question is, how do we wait just the right amount of time? Okay, and do we do wait? Okay, so we've got this joiner object, and we go and find a joiner object. And that joiner object has got a join method that magically blocks us, okay, till all the runnables have, all the child runnables, child expressions have been evaluated by the thread pool workers. So this is a blocking call, just like your read is a blocking call. This is a blocking call. This is a blocking call that you have to implement in terms of the primitive blocking calls provided by the Java thread library, and the Java thread library provides the wait call. And so you got to implement it in terms of that. If you're going to implement a blocking call, you need to also find a way to unblock it. And the Java thread notify method allows you to unblock. So when we go and look, so the implementation joiner has to somehow use wait and notify, which apparently is confusing some of you. And I haven't quite figured out what the exact confusion is. But I can understand why that's complex. Just as recursion is very easy to define, that the routine just calls itself. But using recursion in different ways is challenging. Okay, so I in fact see the same people who had trouble with recursion in the second assignment and then traverse in another assignment are also having trouble with this, and that's because it is difficult. Okay, if you haven't programmed that much. So, but we will see other forms of synchronization soon, and we will maybe get some hints as to how to do those programs. Yeah.
So if we haven't really studied threading or like threads before, do we need to familiarize ourselves with that concept before we even mess with the join?
If you haven't studied threads before, so everything that you have to do is prerequisites covered by me. So I have defined threads in the full detail that you need to use them. Okay. In my lectures, which are represented in the PowerPoints. Okay? And remember, I did threads in two parts. I did threads in the beginning of the course, and then I've continued on later. So there was an overview section where I did prologue, I did ML, I did Veka and I also did threads. Okay? Between that material and this material, you shouldn't have to go and study anything else. My explanations might not be as thorough. I think they're precise enough, but you might need more duplication of the explanation. So go ahead and look at threads from somewhere else if that helps you understand things better. Okay? Okay. So we've got this joiner.join method here, okay, that magically blocks us. And we are going to, at this point, now that we've used up the joiner is something we got from a pool, and we want to return that joiner to the pool before we finish our task. So that's what this return joiner method is. Okay, and that's something I haven't gone and expelled out the details of. And we should also return the workers we got. Okay, so we can go through the loop of the workers, iterate through the loop and return each worker. And so that's the piece of code here. And then, like I said, how threads work, you can go and look up other material, you can go and look up my material. It's not going to be too difficult to figure out how they work. How to use them is the challenging part. So how do threads work? How does the synchronized method work? How do notify and wait work? It's about a few hours of work to go and understand the exact semantics. Okay, you can just go and look up you can just do Java doc and find out. How to use them is challenging. So, and one of the things we have to worry about is multiple threads executing the same piece of code and interfering with each other. So I've given you a solution that works as long as we don't consider interference from other threads. Okay? So code is often classified as regular code and thread-safe code. And so far this code is just regular code, but we have to make it thread-safe, okay? Which means we have to worry about concurrent access. So let's go and see what threads are actually executing the piece of code. So here's let's say that's the initial parent. The parent is going to have to evaluate a list of expressions. So it's going to execute this piece of code, and it's creating and fetching these thread workers. So we'll call them children of this. And these children are not executing do parallel unless they become themselves parents. And they are given lists to evaluate themselves, sublists to evaluate. So we have a giant list to evaluate, and that can go and involve children lists evaluation. So they may become parents later and execute the same do parallel method on the same object because we have a singleton here. So we have also, let's say, T1 results in the thread T11 being executed. The T11 thread can execute in both the child role and the parent role. And in the parent role, it might execute do parallel. So that's what TP11 means here. Okay. So now we have these two threads executing this piece of code. And when does some code become thread unsafe? When it accesses some common data structures. Okay. And we have some common data structures here. We have the thread pool, we have the joiner pool. And they are being accessed here. So we want them to be executed in a thread-safe way, which means that we should synchronize the access. So one way to do that is to just use a synchronized keyword. Okay, we have that. It's easy to go use it and make that method do synchronized. And we saw the problem with this, that we are now, basically that means that when let's say T1 as a parent is executing this method, while it's in the middle of this method, TP11 can't execute the method also. Okay, now as it turns out, when it goes and executes joiner.join, it's going to wait. And when it waits, it will lose the synchronized lock. Okay, so at that point, the child thread can execute the code. But even then, we are locking much more. We are also locking but when it is executing its expression, okay, this runnable 0, at that point, the children thread cannot go and execute this piece of code. They have to wait for it to finish its task before they can execute it. Okay, so we don't want such coarse-grained mutual exclusion. Okay, so we are going to then so forking child blocked by forking parent as long as it's active, as long as it's not waiting. So we want to not put synchronize on that piece of on the whole method. We want to synchronize the things we need to synchronize. Okay, here the getter create worker. At that point we're accessing the worker list, so we should synchronize that, and we should also go and synchronize access to the joiner pool. Okay, so whenever we are accessing the joiner pool or the worker pool, we should synchronize access to that access there. And what we are not synchronizing, which is the most important thing, is this runnable 0.run, because that's where the piece of work is. Apparently this piece of work is complex. That's why we want parallel computation. So while we're doing this piece of work, we don't want other people to be locked out. Okay? So should we call joiner.finish? We call joiner.join. So what is your understanding of the joiner semantics of finish and join? I know it was done a few times, but you might have looked at it. What do you think join means?
So join will wait for a count, that waits for like n threads, and finish will add that number.
So you're telling me an implementation. I don't want to know the implementation. So joiner waits how long? What does the joiner wait for exactly?
Until all the threads are finished.
So if the count is n, it waits for n finished calls.
Yeah.
Semantics are very clear.
Yeah.
Who's going to make the finished call?
The main thread.
This is the parent thread. The parent thread is waiting. The parent thread, so the finish call must unblock. Right? The joiner waits for n finish calls to finish. That means the unblocking has to happen in finish and not in join. So it can't both wait and unblock. So somebody else has to unblock it. And it's waiting for who to finish?
No, I mean, Runnable's 0 is one runnable.
It's a method, it's a piece of code.
It should add that number by 1, and after it is.
Oh, so you're saying that I haven't given the right current number to the joiner?
Or you set the number to be less minus.
Okay, you're right. So my set num thread should be runnables.length minus 1. Right? Yeah, sure. I thought we had, didn't you point out this mistake once before? Or maybe it was in another context. I always confuse between there being n plus 1. So you are indeed right. Okay? That this should be runnables. But there's no finished call here. That's important. Okay. Oh, what you meant was, I get it. What you meant was that if you're doing runnables.length, then you should do a finish yourself also. Right? Maybe that's what you meant. But we should just do runnables.length minus 1. Okay? Good. So, we also saw that with the finish call, we have a problem here that the early worker is idle. Okay, so we are giving these n expressions to evaluate, and this is n plus. So this is the reason why this is sometimes I talk of n plus 1, sometimes I talk of n. So we have given these n expressions to evaluate, and they may take different times to finish. So we are releasing the workers after all workers have finished, rather than after releasing the work right after it finishes. So we went and added another method called finished in the thread pool, and that is called by each worker when it finishes, and that method returns the worker. So we don't return the worker in our do parallel method, we return the worker in the finished method. Now, which thread is going to execute this particular piece of code? This is where concurrency gets confusing. So this is the parent, TP1, it executed the do parallel. So far, it was this thread that went and returned the joiners, returned the workers. Which thread is going to execute this piece of work? Who's going to call finished here? It will be the children. Okay? That's the whole point. As the child finishes, it's going to say, I'm done. And so it is the child. The parent is waiting. So it's blocked, waiting for it. But the child goes and, so now we have this particular thread pool object being executed by concurrent threads for two reasons. One, the do parallel is being executed by a parent and by a child that behaves like a parent. And this particular method is being executed by each child. So even if your list doesn't go and have sublists, this piece of code needs protection in terms of mutual exclusion. Okay? So we want to go and put a lock here too and make it synchronized. Okay? So this is the challenging part, and a lot of code is not thread safe, by the way. and just your generic data structures like lists are not thread safe in Java. Okay, so you need special data types that are actually thread safe. Yeah, you have a question?
But we're also having the parent run like one of the threads, right?
Sorry?
We're also having the parent thread run like basically how the end result should be is the parent thread also be like running a runnable as well.
So what does running a runnable mean? A runnable is a piece of work. Any thread can execute it.
So it's also
So it's just executing the runnable. Okay? So the runnables and threads do different things. Runnables are pieces of work. Threads are workers. Now I've confused that a little bit by calling this thing a worker because it happens to be a manager that delegates work. Okay? But think of how things start. There was one main thread in the beginning. That main thread went and did two parallel. That main thread will also go and do one of the pieces of work. So we didn't create a new thread to do that. That main thread executed one of the runnables. Then it found other threads to do the other runnables. Okay?
I'm just trying to think of like how that would look like. Would that be like incorporated inside like the thread pool? Or would that be kind of like, I'm just like trying to
I'm telling you the whole details here. A runnable is an object with a method called run. I can in a thread execute methods on different objects. It so happens that this particular thread was executing do parallel in the thread pool so far. Then it goes and executes a run method of runnable 0. So there's no magic here. There's absolutely no magic here. It's just going from one method to another method, just as we do in any OO programming. The magic happens in the thread pool worker a little bit. Okay, but this is 401 stuff. Okay, in terms of just sequential code. We're just hopping from object method to object method.
I just didn't like, I don't think I saw like the runnables, the 0 run.
Yeah.
That was kind of like,
That's fine. No, it's okay to be confused. If you aren't confused if you're not trying to understand. Okay. Okay, questions? So now let's go and look at more parent-child coordination. Okay, and this is where again concurrent programming gets tricky. What do we synchronize? Where do we notify? Where do we wait? How do the wait and notifies relate to each other? And I'm trying to draw some general principles from this example because this example is something that we can motivate using our problem. And we did a lot of it last time. And let's try to finish this. We more or less finished it last time, but there's some subtle issues left. Okay. So there's a lot of methods we have to worry about, and we did worry about many of them last time. But let's go and figure out again which methods are executed by which thread. Okay. So threadpool dot create new worker, if you remember, was called by do parallel. Okay. So the thread that did the two parallels also executing create new worker. So that's the parent thread. Okay. Now in that set dynamic runnable, from what you guys remember, which thread is going to execute that?
It's going to be what? What did you say?
So the thread pool worker set dynamic runnable.
So then it probably would be run by pool.
So it's people. This is something that gets very confusing. People confuse between threads and objects. Okay, this happens a lot. And let me just sort of draw an analogy. When we look at the observer pattern, there was an observer object notifying an observable object. That was notify. All done within a thread, and the question was this object notifies this object. When we use wait and notify, we are talking about threads notifying each other. Okay, it's a different word. So we don't go and say which, when I say which thread is executing set dynamic runnable, I don't mean to ask you from which object this particular call was made. I'm trying to ask you which thread is doing this. But you're on the right track here, Andrew. Sorry? Parent thread. Okay? So the parent thread is the one that entered the do parallel. That do parallel calls set dynamic runnable. So we are going to go and call it from the parent thread. No, no, TP1 is the parent.
Oh.
Okay? So we're going to have TP1 set dynamic runnable in the thread pool in the worker. Okay? Quit, thread pool.quit would be called by, sorry? Well, quit is being called, maybe the user goes and says quit at the end. That's probably being processed by the main thread. Okay? So it's probably going to be the topmost, who knows who's going to call quit exactly, because anybody can call quit. But we expect it to be the interpreted thread, so it's probably going to be, so we'll just say it's the parent because main was a thread. And that quit has to result in kills being called, basically all the thread pool workers being killed. Okay? So who's going to call kill then? Whoever called quit. Okay? It depends when we decide to quit. Okay? Quit is this out of band thing. But I'm expecting the quit to be called by the quit command in the Lisp interpreter, which will be the main thread. Okay? So this we'll go and say that it is the initial parent and maybe it's the main. But in general, quit could be called by anybody. Okay? Now let's go and look at threadpool worker.run. Who's going to call this particular method?
Would that be both the parent and the children?
Okay, why the child? Okay, so we've got two answers. Both the parent and the child, just the parent, and there's a third possible answer, just the child. So why did you think both the parent and the child? Why the child?
Oh wait, no,
Don't back off.
I think I was still thinking that this was, so it's run and that's the run function, so then it will, okay, so the third pool worker is what is, that's the runnable, right?
So that's the master data runnable.
Oh, that's the master.
That's the dispatching runnable.
Okay.
Then there are the dispatched runnables.
Okay.
The dispatch runnables are what were passed to the do parallel. Okay? Set dynamic runnable. This is the dispatch runnable that we are going and invoking. This is the dispatcher runnable. Okay? So this is where it gets confusing or interesting. Okay? So the run method and this is where you guys need some practice with threads. The run method, and Robert, who has practice with threads, is going to clarify this, is called by? Called by Java, but which thread? Given that there's parent threads and worker threads.
Well, isn't it called by whatever method creates? It's invoked when you start the thread, but you don't actually call it. It's just invoked when you start the thread, so it's invoked by Java, some Java thread. Okay.
So remember that create new worker, which we'll see soon, is going to do new thread.start. It doesn't call run. It says new thread.start. And start and run, please never confuse them. It can take you 2 weeks, as I know from one student last semester, to go and find a bug in which you did the reverse. Okay, it can take some people 2 weeks at least. So let's go and see create new worker. So this is actually invoked by the child, okay, and let's go and see that. You say worker is assign new thread pool worker. Then you say new thread worker.start. That creates a new thread, a child thread. Now every thread needs to have a method to start its stack frame from. Every thread is a new stack frame. Okay? When the main thread, its start frame starts from the main method. Okay, so the main thread is created by Java. And indeed, Java calls the run method. But the question was which thread executes the run method. Okay, so the main method is executed by the main thread. When I do a new thread worker.start, it's this new thread that executes the run method. Okay, and Java makes it do that. And there's some magic going on there. If you haven't done operating systems implementation of threads, you don't quite understand what's going on there. But that's the magic we won't get into in this course. Okay, so some magic happens, and the stack of and basically it's dealing with stacks in memory, and the stack pointer of that thread happens to be at the run method. Okay, so this run method is executed by the child. Okay, so you were right. I mean, you were more right than him. Okay, at least you gave the choice of child thread. The parent thread is never calling the run method of this runnable that was passed in. It called the run method runnable that it was supposed to honor. That it did.
Is the difference between run and start? Start says that this thread is able to be used, and like we're talking about with ready and running. So that's the run is running. Starting is just saying it can now be either ready or run. So really, start just says ready.
Start does two things. Start first goes and sets its program. Every thread's got a program counter. That's what concurrency means. Concurrency means that two threads can have different program counters. And so it goes and sets its program counter to point to the run method. Okay? And then says, now you're ready. Then the scheduler decides, okay, it's your chance to execute, so you will execute, or somebody else will execute. So that's what's really happening underneath.
So the run method is called implicitly by the user.
But it's called implicitly by yes and no. Start will just go and create a new thread. Okay? And that new thread has to have a stack pointer. It sets its stack pointer to that run method. But that method will not return back to start. It's a new stack. So this is the important thing. That when we say a method calls another method implicitly or explicitly, we are saying that if T is a thread that calls M1, and M1 calls M2, and M2 calls M3, when M3 is called implicitly, all M1, M2, M3 execute in thread T. And M2 returns to M1, M1 returns to M0. Here, thread.start returns before the run method is even called, perhaps. It returns back to that stack, and then we've got a new stack with a new thread, new worker that's gone and is doing its own thing. That is the key difference between forking a thread and doing things synchronously. Okay, within the same thread, the procedure returns back, you wait for it. When you have a new thread, you say, okay, you just carry off, and I'll do that, and then we'll go and synchronize using wait and notify possibly. Andrew.
So the overall goal is we're saving threads to use again later, right? Like what do you think?
Overall goal, comparing our previous solution to this solution, is that we are saving on threads. Creating a new thread is a very expensive operation. So, you can do an assignment straight away. That's cheap. You can call a procedure to do the assignment. That's more expensive. And you can create a thread to do the procedure. That's even more expensive. Or you can create a process to go and do the procedure in a separate address space. That's even more expensive. Okay? There's more isolation when you have another process. There's more performance degradation when you have a new. So the heavier the weight in terms of expense, the more safety there is. But more.
I know you mentioned this previously, but like, isn't like, so the initial thing is like we're trying to make it so each of the things better, right, on their own threads, but then we're also wanting to save the threads.
We want to save on threads.
Okay.
Okay?
So we have like a list or a.
Which is what we have, the queue of thread work and joiners.
And so then we have to have it in the thread worker runnable to have some way to wait until it gets more work.
So that's what we're going to get into. So that is the overall goal. I mean, in terms of application, but I'm a systems guy. Applications don't excite me too much. The internals excite me more. The main goal is to teach you guys some coordination primitives. Bring out some principles that are going to be reused again and again, because if you ever do any real programming, you've got to do multi-threaded. And if you do multi-threaded, you've got to handle these things. Okay? So I don't want to let loose on you guys building Boeing software and not knowing what threads mean and what safety means. Okay? Or even building Microsoft software that can afford to fail. Okay? You don't want it to fail. Okay? So that's the real goal, if you want to ask me. Okay? Okay. So some methods were right. Easy. Constructor just goes and initializes instance variables. No magic there. That's sort of 110 like stuff. Quit goes and calls the kill method in a loop. Again, 110, 401 kind of stuff. 110 actually. Kill is more challenging, and we saw the solution last time, but we'll repeat it again. Now remember, this threadpool worker.run is a runnable. That's the master runnable, the manager runnable, the dispatcher runnable. Okay, and it's going to go and have to shuttle between the dispatched work runnables. Okay, they're all pieces of work. So it's going to take its dynamic runnable, whichever its current dynamic runnable is, and run it. So it's the classic idea of the manager delegating somebody else, right? So it says, I've got to do my work, I'll go and take my dynamic runnable and run it and execute it. This is equivalent of, in the previous slide, the master going and executing the run method. This is what it's doing here. Okay? The master thread, the parent thread was already created, so it went and said, do this run. This threadpool worker thread is already created, and so it's saying, do the run. Okay? It's just a very similar run method call. Okay? Now we know that we should finish after this, so that somebody who's waiting for us can leave. So we'll say joiner.finished. Our joiner got initialized in the constructor. So that's good. We also know that we wanted to release this worker as soon as possible. So we also say threadpool.finished, which will go and release the worker immediately. Okay? And then we also saw last time that after we've done our work, we need to wait for new work, right? So there must be a wait call somewhere. So let's go and, okay. We have to also figure out how to go and finish this loop. Okay, that's what I'm doing next. So we decided that we're not going to just kill the thread unceremoniously. We're going to let it go and finish gracefully. Say, this is your time to go. So before you go, please release your locks, finish your loop, do all the things, and then you will go. So we'll set this variable to be true, and this goes and says, if killed, break. Okay? From the loop. So this is a loop that we didn't give a condition on in the do. So it goes and terminates the loop, and this is again the way to go and kill a thread in general. This is a very general principle I'm teaching you here. Okay? And now we should go and, so because we are accessing a common variable, this should be synchronized, as should this be synchronized. Okay, this is again a principle. Whenever you access a common variable and you know it's going to be accessed by multiple threads, please put it in a synchronized method or synchronized block. Okay? And we should wait after each iteration. So I think my animation is a little off here. But here. So I went and did a wait here. Okay? That seems reasonable? Yeah.
Why is a queue variable shared by I think it should be
Which variable is shared? Where have I accessed a queue variable here?
so why should it be lock on
Killed. Oh, because who's going to kill me? Maybe the main thread. Somebody else is going and saying, I mean, it's not suicide, right? It's kill. It's murder. Somebody else is doing it to you. You're just executing a run method. That's all you care about. The user went and typed quit. That quit is processed by the main thread. The main thread goes in, says, kill.
this queue is queuing this special worker, not the whole thread pool, right?
Exactly. But the worker is an object. This is the object. It's got a killed instance variable. That instance variable is being accessed both by the child thread, if killed break, and accessed by somebody who's killing you. And let's go and have a safe kill. They're two different threads. Okay?
Is this because when we're doing quit, we're going to do for every worker in the queue, we're going to kill, and you don't want to do them all at the same time, so it's synchronized, so there's one, and then does the other, is that why?
The why is because there are two threads. Why do you not allow two cars to go and enter the intersection at the same time? Okay? There's got to be, and we saw, please go and look at previous slides when we saw what happens when we don't synchronize. Okay? That we saw that we would get results where I would load something in a register, somebody else would go in, and as it turns out, one person's reading and the other person's writing, so it's not too bad here. If two people are writing, it becomes much worse. Okay? And kill can probably be done atomically anyway, so we don't get into an inconsistent state. But in general, it's a good principle to go and make sure the readers, even the reader and writer, supposing you're accessing 3 variables in an object, you want to make sure all 3 variables are changed before anyone reads a value. As it turns out, you can get away without doing kill, okay? Because kill is just one variable, it's not an object. But it's just good discipline that whenever you're accessing shared variable, and a variable is shared if 2 different threads go and access it, okay? If all threads just read it, then there's no problem, okay? But if it's if some read it and some write it, then you should synchronize. Yeah.
Okay, we know. So is it because it wants to read, like you were talking about read and write? So it wants to read it, but because it's currently being edited and it's not edited, like at a split second, it needs the time for the computer to edit it. So once it's finally edited, then you can read it. Because if it's not finished editing, that's bad. But if it tries to read it while it still says true, then it'll keep going, even though you didn't want to keep going and do bad things. So is that like what you're trying to say with like the synchronization?
Exactly. That is what we're trying to say, that things should be consistent. So in general, every object has an invariant. An invariant means that, supposing you have a queue and you add an element, you also change a pointer, right? So the new element addition and the pointer movement will occur one thing at a time. But to the external person, they shouldn't be inconsistent with each other. So if it's an atomic value, as it turns out, no real harm is going to happen if you understand how the implementation works. But whenever there's a composite data structure like that, you have to worry about it. And that's why I said that Java lists and Java sets are not thread safe. Okay, you have to go and use thread safe equivalents of them to go and make sure that bad things don't happen. Okay, so I'm trying to show you how to create thread safe code, and that requires us to think about, which thread is executing which piece of code. Nothing is dumb.
This ThreadPool stuff, this already exists in Java, or is this stuff that we have to be making? Like, if I were to do this outside of this class, and I want to make something thread-safe, like you're talking about, could I just use ThreadPools?
So does this piece of code exist in Java or not?
Yeah.
The way I've defined it, no. Okay? And we aren't giving it to you, so you have to implement it.
Yeah.
Okay? But the way I've defined it, so there was this question that you asked last time, that here we are being pushed work. Okay, the ThreadPool worker is being pushed work, and the ThreadPool worker could have also pulled work. If it would have pulled, it needed to pull 2 things: the runnable and a joiner, and somehow they have to be coordinated with each other, which would make coding, and I believe we haven't tried it, more tricky. So that's why we are pushing it, because the parent has done both things, so the parent is just pushing these things there. So if you look at Java implementations, they are based on this no joiner associated with the ThreadPool, and so the joiner object is our own, and the ThreadPool work is our own, and it's good that it's our own, because we can think about how these things work from first principles.
So I'm just trying to think, so you have the parent thread and makes 2 child threads per second. So the parent thread kills the first child and kind of starts running that.
Hang on, say that slowly.
Okay,
So the parent thread went and found 2 new workers.
Yeah, so the parent thread has 2 tasks. So would it make 1 new worker go to the top? And I'm just trying to think, if it then makes 2 more, it's after those finish, then it then calls kill both of those.
It doesn't call, kill is something that Andrew put in, and I didn't want to discuss it, but it's there. Kill is not the same as join. If you're going to kill the threads, then what is the point of creating these reusable threads?
Yeah.
Kill is done when you do quit. Lisp has a command called quit. And before quitting, we want data set to be killed, cleaned up, so we are calling kill for that reason. Or at some point so this is just something that
So if we're doing this in Lisp, we would have, so basically we would kill at the very end of say we do load test on Lisp. There would be a final.
there's a quit command. There's a quit command in Lisp.
Okay.
The quit command has got an evaluator that will call kill. That'll do quit. Okay. As it turns out,
And that's how we end Lisp basically.
and you don't really have to do it. It's like you don't have to clean up because somebody else might clean up after you. So you can just, the process when it finishes, everything is gone anyway. Who cared? Okay? But if we wanted to finish the thread pool and start a new phase, like, create a new thread pool afterwards, we want to reuse, then kill will be useful. So kill is not that useful as such, but kill is a very good concept to have in general. So I wanted to show you how kill is implemented for that reason.
Then would we have to implement like a quit evaluator?
Which already exists and you have to replace it. Okay? Yeah, it exists. Okay. So far so good? You guys happy that we are waiting after kill for new work? You're the one who said it last time, okay? After piece of work, the threadpool worker has finished work. Who knows when the user is going to enter the next command? It can't just go on in a loop, okay? So what happens if I don't put the wait? If I don't put this wait here, it'll go back here and do what? Execute the same dynamic runnable again. Okay? So we have two problems going on here. Firstly, we're going in a loop and executing it again and again and again. It's called busy waiting. Okay? Secondly, we are doing the same piece of work. This particular runnable might have side effects. We are doing the side effects multiple times. So a wait call makes sense. Who's going to unblock the wait? Who's going to unblock this guy? So who's that? Set dynamic runnable. Okay? That's going to unblock it. And now I'm going to claim this doesn't work. Yeah. Good question. Whenever you do things in a loop, you have to worry about should you do them in the beginning or in the end. And I've already hinted that this is wrong. Why is it wrong? Why should we do it in the beginning? So let's look at the sequence of actions. The parent went and did create new worker, okay? And then the parent went and set dynamic runnable, right? And the runnable, this particular piece of code results in the run method being called. So what can happen? The parent says create new worker. The parent is going to then do set dynamic runnable. That's what it's doing. At this point, the new runnable started. Okay? The parent is going to take its time. At this point, the operating system says, oh, I've got only one processor. A new child has been created. Let's give the child the processor. So the parent goes and is put in the ready queue. It's no longer current. And the thread pool worker is the current one. It comes here, and if the parent is given a chance, it will go and set the dynamic runnable, but it never got a chance. And so this guy goes and calls run method on a null. It's going to get a null pointer exception. And plus you have it, and what you really need is a wait. Okay? So the parent is late, and the child is early. Okay, so we have to consider two cases, the parent being early and the child being early. Okay? So if the child is early, it's going to go and execute this run method without doing a wait. Okay? So we should go and by the way, so this is the notify is happening here. Okay? So early child, parent setting dynamic runnable may not have been scheduled when worker executes loop for the first time. It takes me forever to make these slides for this reason. Okay. Good? All happy? Still doesn't work. So we have two conditions, parent early, child early, and nothing of early parent. The parent comes in, it creates a new thread, The operating system says, hey, the parent has got work to do. I'm going to schedule the parent. I'll execute the child whenever it wants, whenever it needs to be executed. Okay, this is where you guys, if you understand this, you guys really understand wait and signal, wait and notify. So the parent comes in, and the parent calls set dynamic runnable before this particular piece run has been even executed. What it's going to do is going to go and set these variables and do notify. Is anybody waiting for the notify? This guy haven't even executed run. So when he comes to wait, he's not going to get a notify. The notify has been lost. The child is created, but the child has not run. The start just creates a ready child. The child is not running as yet. So what should we do? So this is the key here. Never do a wait unguarded. I should say never, right? But a wait should be preceded by some condition. You should always check some variable. You're always waiting on some condition. All wait does is give you a way to block. You need to associate that with some condition, some instance variable whose value you check before you decide to go and wait or not. And notify should always occur after you've gone and changed that variable. That's a general principle. So in this case, the notify occurred after which variable, the relevant variable that you changed? Dynamic runnable. So what should you check before wait? And you should check if it is?
Assuming that we're resetting its value.
Okay, firstly, we have to go in. Okay, before we even go there, we have to go in. Whenever we do notifies and, okay, so before we go there, let me just, exactly, Robert's got the whole answer here. But before we talk about it, remember, wait and notify should always be done in synchronized methods. Why? Because they both access a queue of threads. And we just said that queues should be protected via synchronized methods. So if you don't do that, Java will complain on you. So, it'll say, sorry, you're not doing this synchronized. So I can go and synchronize my constructor because I'm notifying there. And I can synchronize my run method. And I'm going to argue that this is not a good thing to do. I mean, it's a good thing to do, but it's not as good as you can be. In fact, you should never synchronize your run method. No, the the number of workers that run depends on the number of processors.
It means that the lock on an object is never going to be true.
Yeah, basically, once you're executing a run method, unless you do a wait, nobody can enter the object. So the same reasons that we showed earlier, we want to have not the lock here, but here, somewhere here. Let us not go and lock dynamic runnable.run. That is the main idea.
What you're saying, make a separate function that has a lock in it?
That's the best thing to do. Or you can do synchronize this. I don't like synchronize this as I've never used them in my life. They exist because people are too lazy to write procedures. But I'm not too lazy to write procedures. At least most of the time. Okay? Sorry? We don't want to lock on this dynamic runnable.run. Okay, because that's
On the left side.
Because we are just doing, all we are doing is notify and changing one variable. And we do want them to be occur together. Okay? So now we go back to the previous question. How do we guard wait? Early parent. Parent may do first notify before worker does first wait for dynamic runnable assignment. Okay? That's what we said already. I'm just putting that in text. So we go and set if dynamical runnable equals null, wait. And now Robert said something after that, and I don't know how many of you got that, but this is not enough. What's going to happen? The first time you'll do a wait, you do dynamic runnable.run, and you come back here, and you still find dynamic runnable to be not null. So you won't wait. The first wait will occur, but the second wait will not occur. Right? The way of so by the way, if you're checking dynamic runnable, put a lock there too, and we have to go and set dynamic runnable to okay. Just one slide. That's all we've done today. But you guys have learned a lot. Okay? I don't have no empty slots left here, so I think we finished.
So I'm still kind of unhappy.
Sorry?
I actually don't like this though, because if let's say I'm done and I'm waiting, and the main goes to kill me, I never unblock, so I don't actually clean up. Yeah, somehow that runnable has that thread has to be.
Sorry. So how will we fix this? Actually, I didn't have space for it. You know, it's like the Fermat's last theorem. I didn't have space. Sorry? Actually, no. Actually, I'm right. Just like Fermat. You could notify it, and so maybe what you need to do is you need to go and say killed equals true, and then say notify. That's good. That's good.
It feels dangerous.
If that was true, and then dynamically would run the current dynamic runnable again, though, and that's busy.
No, he's waiting on.
Yeah, you would need to modify. Yeah, you need to modify your control.
Yeah.
The kill method will just do notify after that.
Yeah, but then it will, so since the weight's up at the top, it does busy.
And you should go and then at this point check if killed.
Yeah.
You should go and check if killed.
And then build break. Okay, yeah.
Yeah. Okay, so we should move the killed to after wait. Guys get that? If you're blocked on the wait, then if somebody goes and kills you, you don't ever unblock to go and check the kill variable. Okay? So what you should really do is, right after, so here you should do a notify, and right after the wait you should go and do if killed, then break.
Couldn't we get the same weaving issue where the notify doesn't actually get to the wait? So don't we have to notify? Because we could have a scenario where we check if killed and it hasn't been killed, but then the notify happens and then we wait.
It's the same thing you're talking about with the set dynamic runnable needing to have a variable for a nibble.
No, that's what we have. We have if killed, right?
Before it, then wait, then
Well, no. Oh, if we're all synchronized.
Yeah. This is synchronized. Okay. Yes. If kill break should be done after break. Okay. And this should have killed equals true and notify. I'll try to go and do this. Probably not. Because we'll go up. From here, we'll go up there. And so after we've done, I mean, it depends on how quickly we want it done, right? So while we're doing this piece of work, I don't think it'll make a difference. Okay, in fact, you should be killed before you've done any work. Okay, or after you've done any work. Either way, it's all right. The difference is that the last piece of work may not be done if you do this. But then, this whole killing threads is actually a very tricky issue to get it right. Okay, what does it really mean? Okay, so, yeah. Okay. Questions? Okay, if you guys understand this, or if you eventually understand this, you've understood a lot about concurrency. Okay. And weight is conditional or a condition variable set by notifier to prevent race conditions between it and its unblocking notifier, which is kind of what I want. And I'm just going to go through these principles because I've already set them out, but this is just when you guys look at the PDFs, you have text to go and understand. I couldn't put all the text in the previous slide, but this is something I have gone and said. Okay, and eager settings, we have eager normal, and then we have when you're in eager mode, whether you want eager pool or not want eager pool. So that's an option here. And we saw that with eager evaluation, if you want deterministic evaluation, we want deep copy. Okay, we saw that previously. So this is just summarizing this. Yeah.
So the dynamic runnable of a strategy motor is set to be not empty, and before it's run, the parent costs Q. Then we never get a chance to return this.
Yes. Yes. Yeah. So we don't know. Kill is just who knows what should be the right answer there. Okay, this is something that concurrent people have never been able to figure out. And that's why there is a kill, by the way, in the thread library. You can just say thread.kill. And if you use it, they'll say, hey, you're being bad. Okay, and people will never go and resolve what kill really means. Okay, so yes, there's all kinds of issues that can occur there.
So basically what it's all doing is after when it kills kernel, it just sets it to both, it stops the runnable from running, and which puts the runnable and the thread, the garbage collector, basically.
The thread is just finished. The thread gets out of the queue.
The finishes the run's finished.
Right.
So it gets at the
So if the runnable, the thread object, there's a thread object, there's a runnable object. The runnable object will be garbage collected only once.
once it finishes running.
When somebody else still might have a reference to a runnable object. So how garbage collection occurs is, how many references you have. Okay, and how do we know that we are executing things right? Well, let's go and look at this program here. So one of the things we've added is a print thread basic function that goes and prints out the current thread. Okay, and what is this piece of code doing? So by the way, we've also added new code. Andrew's been quite busy, and we've got set eval mode, normal, eager, and even lazy. Lazy is more or less finished, but it's only appropriate that lazy is more or less finished and not completely finished, right? So we have set eval mode normal, and then I'm doing list, and prog_n is something else that Andrew has. It's just like let without initializing any variables. So basically it has the expression that is going to be the return value, which is +1, 2. In addition, some optional expressions that you execute before that. Okay. So I'm doing list of +1, 2 and +-2, 1. Okay. And before I do +2, 1 and -2, 1 each, I go and print out the threads. Okay. And I do that once, and I do the same list thing again later. Okay. So the main interpreter is first told execute set eval mode normal, then it goes and evaluates this list, then it's told to evaluate the list again. Okay. What you expect the output to be in both cases is 3, 1, right? The list consists of +2, 1 and -2, 1, so that's 3, 1. And the printouts that we see here, do they convince you this is serial execution? Every one of those prints was executed by the main thread. We didn't create any threads. Okay, when you do eager pool nil but eager mode, what happens? One of those expressions here is done by main 5. The other one is done by a new thread created, which we are calling, which is lambda 0. Then again, the second one, the main thread again executes the first expression. It creates yet another thread, which is lambda eval 1, to do the next one. So this is the non-thread pool. Set eager mode. This is the regular credit. You get this done, you got your regular credit going. You got your joiner working. That's good enough, by the way. That's pretty good. Nothing is good enough. That's pretty good. Okay? And this is the thread pool. Okay? We used thread pool worker 05 there. We use the thread pool worker 05 there again. Now, see how things got switched here? The 05 finished earlier than the main. Okay? So, indeed, these race conditions occur in real practice. Okay?